Okay, low control roll, 4.5. Here we go. Let me get this focused again. Alrighty. So let's look at the limit as x approaches 1 of ln x over x squared minus 1. You just thought they were going away, didn't you? Joke's on you. Okay, what is it? No. What is this when you plug in a 1? What's the ln of 1? 0. What's x over minus 1? 0. Okay, this form, I don't know if I think we did name it. What's it called? No. Starts with an I. N. Oh, it's indeterminate form. Indeterminate form. Alright, so here's what we're going to do. If we looked at both of these functions, here's ln x, here's x squared minus 1 at 1. The slope here is, no, hang on, I'm getting ahead of myself. If we look at what the function's approaching approaching 0, and this function is approaching 0 also, which is how we got 0 over 0, right? Okay, let's say instead of looking at the function that we look at the linearization of the function. We look at the linear approximation of the function, which just dawns on me. I don't think we talked very extensively about linear approximation. Which is great. Linear approximation is basically just finding the equation of the tangent line. So I'm saying if I can take this function and instead of looking at the whole function, since I'm talking about x approaches 1, let's zoom in and let's just look at what the linearization, what the linear function would be if we could make one. Okay? Now, I drew it. You can kind of see it. It's a little bit dark. I drew it. Do you think, is the limit the same on the linear function as it is on the regular function? As x approaches 1? Yes. See, it's still going to 0. This is like the linear function. So as x approaches 1, the linear function is still approaching 0. So I didn't change the limit, right? It's the same. Same thing over here. If I could take this, and if I could find the linearization of this function, is the limit going to be the same? Is it still 0? Yes, it is. Okay, so what would the limit of this function be? Or what would the linearization of this function be? I know that this is ln x. What's the derivative?
1 over x.
1 over x. What would the equation of the tangent line be? Y. Okay, what's the point? It's 1 comma what? 0. So it'd be y minus 0 equals 1 times x minus 1. Thank you. Yes? Yes. Okay, what about this one over here? So y is equal to x squared. The derivative would be 2x. The equation of the point is 1 comma 0. And what would the equation be? It's going to be y minus 0 equals 2 times x minus 1. So what I'm going to propose is that we look at this instead of the way it was, the limit as x approaches 1 of ln x over x squared minus 1. Instead we say this must also be equal, thank you, this must also be equal to the limit as x approaches 1 of 1 times x minus 1 over 2 times x minus 1. Do you agree?
Yeah.
Everyone follow.
Oh, yes.
What happens? Okay, now, this is crazy that it worked, but maybe I just picked a really good example. So let's think about globally what this means. So think about what we did. Okay, first of all, we started this process because we got 0 over 0. That means that both of these functions have the same point in common. We're approaching an x value and we're getting the y value as 0. So they both have to have this same point in common. Also, what do we know about this point? What do we know about the y coordinate specifically? It's always going to be 0 because that's how we got in this predicament in the first place, was because we got 0 over 0. So we always have the same point and the y value is always 0. Think about what that does to the equation of the tangent line. You're always just going to have y equals slope times x minus 1. Or minus some x sub 1. We'll say point. You're always going to have that for both of them. So when you put them over each other, notice that the other equation is always going to have this same x minus x1. Why is that? Because it's the same point, so you're going to end up getting the slopes over the slope every time. So that means if the limit as x approaches a of a function over a function equals 0 over 0, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. So if we get 0 over 0, we can look at the linearization of the line. Are you good?
Yeah.
Okay. It's pretty awesome, isn't it? L'Hopital was pretty smart. He was, after all, the one that came up with it. All right, so let's do a couple. What did you say? Of course not. Let me do a couple more examples. Limit as x approaches 0 of sine x over x. The first thing you do when you're finding the limit is always plug it in.
0 over 0, okay.
We get 0 over 0. So this time we're actually going to take the derivative because all we need to find is the slope at 0. So we have the limit as x approaches 0 of sine x over x is equal to the limit as x approaches 0 of, what's the derivative of sine x? Cosine x over the derivative of x? 1. And what is this limit as x approaches 0? It's 1. Do y'all remember graphing cosine like a billion times in the summer? What is it at 0? Definitely 1. Wouldn't it have been nice to know this when we did limit? Although, we didn't know how to do derivatives back then. But then there's always a reason. There's always a reason why you can't know it early. Okay, so here we get, what? This should probably be negative 2. No, 2. No, this should be x squared minus 4. I'm sorry, I lied. Right there. X squared minus 4. Okay, so what happens when you plug in 2? 0 is 0. Do you remember what we used to do about this? No. No.
We did the bigger number or something?
No. 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 Stop. Stop. Yes. In the past, when we got 0 to 0, we always algebraically manipulated, which usually meant factor. Sometimes it meant multiplying by the conjugate or something like that. So, we don't have to do that anymore, which would be really nice for the ones that have square roots and stuff. But anyway, so we can know that the limit of this is going to be equal to the limit as x approaches 2 of 2x over 2x minus 5, which is over -1, which is -4. Now, let's say you were to take the derivative and actually get 0 over 0 again. Then what? Take the derivatives again. You can keep doing this process. Okay, homework is going to be 9.3. Number 1, 3, 5, 7, 11, 13, 15. And then I'm going to tell you for the other sections which ones did